All right, this is 2.7 derivatives and rates of change. I am only going to do some of the problems in 2.8 just to save some time so that you guys can have time to work on your homework. All right, so 2.7, we're going to talk about what a derivative is and how or why it means the rate of change. So your tangent line, we learned about tangent last year, to the curve of whatever function we're looking at a specific point has a slope that is defined using limit notation. So notice that this resembles our original slope equation from Algebra 1, where we had y2 minus y1 over x2 minus x1. So your tangent line, when we're talking about derivatives, really is just the slope of the line. All right, so first example is we are going to find the equation of a tangent line to our parent function of a parabola y equals x squared at the specific point 1, 1. So that is your x value, your y value, but for our limit notation, this will be the a. So the a that we are approaching in this case is positive 1. All right, so our a is 1. Our function that we are looking at is x squared. And using that limit notation, we are going to write this as the limit as x approaches positive 1. And then one other thing that I want to write for you guys that I should have added in your guided notes is another way to write our limit notation is as h approaches 0. We can write this, and this will be important for future examples in 2.7. Okay, so all of this means the same thing. All right, so here is our function. We want f of x is going to be the first part of our limit notation. Well, f of x in this case is an x squared. Then we have, okay, so this is that x squared. Then we have minus f of a. So when we plug a into our original function, what do we get? Well, in this case, it is also a positive 1. All right, so we have x squared minus 1. Again, that is coming from f of a over x minus a. Well, we don't know what x is. That's just going to be our variable. Minus a in this case. Again, we are approaching that positive 1. All right, so I'm going to erase these colors here. That was 2. Going to erase these colors and just write this so it's nice and neat when I post this on Classroom. All right, so here's my limit notation. From there, I'm going to see if I can simplify anything. Well, we know how to factor. We can factor the numerator to be an x plus 1, x minus 1, all over x minus 1. We see that your x minus 1s will eliminate. So you're left with the limit of x approaches 1 for x plus 1. And now we know that x plus 1, that's a polynomial, so it's continuous, so we can evaluate this. So you are going to take that 1 and evaluate, and you get 1 plus 1 equals 2. Okay, and again, this is your slope of your tangent line, which is your derivative. So I'm going to write that as m sub tan so that we can keep our work organized. M just means slope. Tan just means it's the slope of that tangent line. Okay, so if it just asks you to find the slope of the tangent line, that would be your final answer. But it is asking us to find the equation. So we need to tap back into our Algebra 1 skills. How do we write an equation of a line? Well, you need your slope and you need a point. And from there, you can use point slope form. Okay, so we have y minus the y value. Our y value for our point is positive 1. Our slope we just found is that positive 2 times x minus your x value, which we're approaching positive 1. And then I want you to put this into slope-intercept form. So distribute your 2, combine your like terms, and we will get that our equation of our tangent line is 2x minus 1. Okay, so that's our first example. Now, the reason I had us write up here, this limit notation is because on our next example, we're going to use that to find the equation of our tangent line. Okay, this is called your definition of a derivative using limit notation. Okay, so again, you want to know what your A is going to be. All right, so in this case, what are we approaching? Well, we're approaching positive 3. Okay, so using your definition of a derivative, that limit notation, we have the limit as h approaches 0. For f of a plus h, so up here, f of a plus h, well, we have this 3 over x. That's going to be your function, but instead of trying to add a to that and making it super complicated, what we are going to do is we have our a, which is 3, and we're going to say, well, we would add h to our function there. Okay, so f of 3 plus h minus f of 3 all over h. So again, that's coming directly from your definition of a derivative, that limit notation. And then from there, we are going to substitute in this 3 plus h. We're going to substitute in our f of 3. So what that looks like, we have limit as h approaches 0, f of 3 plus h. Well, that means you're substituting 3 plus h wherever you have an x in your function. So instead of having 3 over x, I'm going to have 3 over 3 plus h minus f of 3. Well, f of 3 is your y value at 3, so that's 1 divided by h. We want a common denominator to be able to simplify the numerator. Okay, so how do I make a whole number, this minus 1, have the same denominator as the 3 over 3 plus h? I'm going to write this as 3 plus h over 3 plus h. Okay, so when I do that, I really have the limit as h approaches 0 for 3 over 3 plus h minus 3 plus h over 3 plus h. Again, I'm rewriting that 1. Okay, from there, I'm going to do 3 minus the 3 plus h, make this all one big fraction in my numerator, but this is distributing a negative sign to my two terms. So when I rewrite this, I'm going to have 3 minus h over 3 plus h all over h. Again, just simplifying everything. Now, what should happen is we are going to eliminate everything that does not have an h. Okay, so in my numerator, so 3 minus 3 gives you 0. You have a negative h over 3 plus h divided by h. Okay, there's nothing else I can combine, so I'm going to keep change flip. Okay, so really this h is h over 1, so I'm going to keep negative h over 3 plus h times, so keep change and then flip. Excuse me. To make that 1 over h. Your h's now cancel. You are left with the limit as h approaches 0 for negative 1 over 3 plus h. And now if I go to evaluate my rational function at 0, I do not have to worry about 0 being in my denominator. So the reason I had to go through and simplify all of this is because if I go back to my original function for my definition of a derivative and I try to evaluate at 0, I'm going to have 0 in the denominator, which is undefined. Okay, but now since I've simplified everything, I've combined everything, I can evaluate at 0, which means I have negative 1 over 3 plus 0, where I get negative 1/3. Now, what did we just find? Well, we just found that your slope of your tangent line is negative 1/3. Again, they want us to find the equation of our tangent line. And that equation comes from your point slope form. So you need a point that falls on this graph. which is that 3 comma 1. And from there, we can use our point slope form to find the equation of a tangent line. Okay, so I'm going to plug this in. Y minus 1 equals, what's my slope? We just found it's negative 1/3. X minus 3. And my little arrow to show what it simplifies down to is y equals negative 1/3 x plus 2. Okay, so again, that is your definition of a derivative. What this means for your graph is, let's say I have this curve that looks maybe something like our sine graph. Tangent line means for a specific graph is we have a line that touches our curve at exactly 1 point. Okay, so we're trying to find that specific line, the equation of that line. So if you look at y equals x squared, okay, if we draw this curve, we know that it looks something like this U shape. If I'm looking at exactly the point 1, 1, I want the tangent line. Okay, and that looks to be about y equals 2x minus 1. Okay, so you could look at the graph of 3 over x. If we find the point 3, 1 and create that tangent line means it only touches your curve at that point, nowhere else. Okay, your position function in general. Suppose an object moves along a straight line according to an equation of motion, which we would label as S. That's your position function. S is the displacement directed distance of the object from the origin at time t. Okay, so instead of having f of x, we have f of t. T represents your time, S represents your position. The function f that describes the motion is called the position function. Now what I want you to do is I should have had a line that goes and splits that here, and same thing here. This is your instantaneous, that's not spelled right, instantaneous velocity. Okay, so if you've taken physics, you should have seen position functions, your velocity functions, acceleration functions. Our velocity function is actually the derivative to your position function. Okay, so we have v of a is equal to the slope. Could be your slope of your tangent line for your position function. Again, notice that we're using that limit definition of a derivative. So let's take a look at one of our application problems we might see. So suppose that a ball is dropped from the upper observation deck of the CN Tower. It's 450 meters above ground. I also want you to add, this should have been typed in, where the position is represented by S of t equals 4.9 t squared. Okay, so that's my position function. What is the velocity after 5 seconds? Okay, so if I find the derivative of my position function, that is going to equal my velocity function. So I want to find v of a. And then once I find v of a, I am going to then evaluate that at 5 because I know that 5 seconds has passed. Okay, so I'm using that limit definition. So the limit as h approaches 0 for f of a plus h minus f of a all over h. Okay, that's your limit definition. So I'm going to take my original function, and instead of having t there, I am going to substitute an a plus h. Okay, so I have 4.9. Instead of having t squared, I'm really going to have an a plus h squared. Okay, so that's the f of a plus h. Minus f of a. Well, f of a in this case is going to be my 4.9 a squared. Okay, so I'm taking that original function 4.9 t squared and substituting that in with an a all over h. Now when I expand my numerator, everything that has an h or everything that does not have an h should eliminate. Okay, so a plus h squared, that means you're going to FOIL that, and you should get 4.9 times a squared plus 2ah plus h squared minus 4.9a squared all over h. And I should be writing limit as h approaches 0. This is formal. Okay, we will eventually learn a shortcut, but for now, this is why it works. Okay, from there, where am I? Okay, from there, I see in my numerator, I can factor out a 4.9 from each term. So this first part is one term, since my 4.9 is being multiplied to my trinomial, and I have a 4.9 multiplied to my a squared. So I'm going to factor out that 4.9, and what's going to be left is a squared plus 2ah plus h squared minus a squared all over h. Okay, inside of my brackets, my a squareds eliminate. Okay, then I'm left with the limit as h approaches 0. I have my 4.9. Everything inside has an h. So I can factor again, and I'm going to factor out that h. And I'm trying to simplify this to see, is there a way that I can eliminate the h in my denominator? When you use the limit definition of a derivative, it should always happen. If it does not, then you've made a mistake somewhere in your algebra. Okay, so I'm going to factor out that h. I'm left with 2a plus h inside of my brackets. And now I see that I have an h on top and h on bottom. So I have limit as h approaches 0 is 4.9 times 2a plus h. I can now evaluate at 0, plug my 0 in, and I get 4.9 times 2a plus 0, or just 4.9 times 2a, which is 9.8a. That is your velocity function. But this specific question is asking after 5 seconds, so we now need to evaluate that at 5. Okay, so v of 5 means I'm plugging in 5, and I get 49 meters per second? Yeah, 49 meters per second. Okay, so after 5 seconds, our ball is traveling at 49 meters per second. I know that meters is my units because we were talking about 450 meters above the ground. All right, how fast is the ball traveling when it hits the ground? So now I care about my position function. This is talking about a specific spot. Okay, so I know that my position function, s of t, is equal to 4.9 t squared. Okay, I want my position to equal 450. Okay, I'm going to solve for t, figure out how many seconds has passed once I hit 450 meters. Now your position, again, we're talking about like the distance. We started 450 meters above. Now I want to know how long does it take for the ball to travel that 450 meters. Okay, when I solve for this, I'm going to do 450 divided by 4.9. That does not work out nicely. I'm going to leave that as a fraction. That equals t squared. To get rid of my exponents, I'm going to take the square root of both sides. But when you take the square root, you always have to account for your negative square root. But in this case, t is talking about time, so I don't care about the negative. So really, your t, it's going to be the square root of 450 over 4.9. Which if we plug that into the calculator, you should get roughly 9.58 seconds. It's not an exact answer, but it's also asking how fast is that? Okay, so yes, I needed to know my position. I know my position, I'm going to be falling, or the ball's going to be falling 450 meters down. Once it hits the ground, it's taken 9.58 seconds. From there, to figure out how fast it was traveling, actually, I want you guys to have the exact answer. So instead of plugging in that 9.58, we're going to plug in the square root of 450 divided by 4.9 into our velocity function, which our velocity function is 9.8 times A. A in this case is that square root of 450 divided by 4.9. So your velocity here, 9.8 times, that is going to be 93.915 meters per second. You could round that up to 94. I have not explicitly said if I want whole numbers or what, but final answer would be 93.915 meters per second. Now what I'm going to do is I'm going to hit done so it saves those examples just to be sure, and let's flip to the back. All right, so again, very similar. If you want to find the derivative that is talking about the slope of your tangent line, we have not learned a shortcut. We're still going to use that limit definition of a derivative. All right, we care about at the number 3. So we have find the derivative of the function x squared minus 8x plus 9 at the number 3. This is talking about your a value. All right, so a is going to equal 3. A equals 3. I also want to know what f of a is. In this case, f of 3. When you plug 3 in for x in your function, you should get -6. Okay, the reason why I need that is because in part B, when it asks for the equation of your tangent line, you need a slope and you need a point. Okay, so let's find our derivative. So f prime of a, I don't think I've explicitly said that. When you have that apostrophe, that is your derivative notation. That apostrophe means f prime, or the derivative of your function at a, is going to be, you are going to look at your original function. Instead of having an x, you're going to have an a plus h. So I have a plus h squared minus 8 times a plus h plus 9. Then I'm subtracting my original function, a squared minus 8a plus 9. Again, I should have my limit notation, the limit as x approaches 3, or we could say as h approaches 0. Okay, all over h. Now one thing, I should have given you guys a little bit more room. This a plus h squared, again, means that you're going to FOIL that, okay, because a plus h squared is a plus h times a plus h. So this is really an a squared plus 2ah plus h squared. You could distribute that -8a, or that -8 to the a and the plus h. So when I do this, I want you guys to be able to know where these values are coming from. Okay, so in my numerator, I really have an a squared plus 2ah plus h squared minus 8a minus 8h plus 9 minus a squared plus 8a, be careful with your signs here, minus 9. Now again, what should happen is anything that does not have an h should eliminate. So this a squared, somewhere in my numerator, should be in minus 8a squared. This negative 8a, there should be a positive 8a, same with my positive 9 and my negative 9. So now once I see everything that eliminates, limit as h approaches 0, I have 2ah plus h squared minus 8h all over h. Factor out your h. You have 2a plus h minus 8 all over h. I see that now my h's cancel out, so I have no h in my denominator, and I can evaluate when h is 0. So what's going to happen is you're left with the limit as h approaches 0 is really 2a minus 8. Let me just write that as 2a minus 8 since I already evaluated that at h. And that is your derivative of your function. Okay, we also need to plug in our 3 to figure out what your derivative is equal to at 3. So I have 2 times 3 minus 8. 6 minus 8 means -2. Your derivative of your function is your slope of your tangent line. So m tangent in this case is -2. We said that f of 3 for your point is -6. Okay, you could also write that as 3 -6 if that helps. Your equation of your tangent line comes from point slope form. So I have y plus 6 equals -2 times x minus 3. When I put this in slope intercept form, you have just y equals -2x. Okay, I think I am going to skip over these instantaneous rate of change application problems, and we will do that on Tuesday. Okay, let's move on to 2 examples from 2.8, and then the rest will also be on Tuesday. Okay, so I think on Google Classroom, I'll have to double check, I'm not sure. You guys will not have a quiz on Tuesday. We will go through this, and then I will put an update on Google Classroom to make sure that we are where we need to be for our schedule. All right, so 2.8, the derivative of a function. We kind of already talked about what this means for your original graph. So your tangent line, or the slope of the tangent line, remember we're looking for a line that will touch your curve at one spot and one spot only. I know that once we get to this part of our curve down at the bottom, we would hit that again, but we're talking about just hitting this one point. All right, so what if I want you to graph the derivative of your function? How do we do that? Well, your trick is always look to see where your slope of your tangent line would be 0. Okay, so when you have a slope of 0, that means that you have a horizontal line. I see that in 3 different spots of my original function, I would have a slope of 0. Okay, so again, I want my line to only touch my graph one time. Okay, I'm not going to go and make a curve. I'm not going directly through my curve. I want it to get very, very, very close, touch once, and then continue on. Okay, so where your slope is equal to 0 for your function f of x, this tells us where your derivative, or f prime of x, has zeros, so where it's crossing your x-axis. Okay, so if I come over here and I draw a graph, I have a slope of 0 on my original function at about 1/2. Okay, so I'm going to have a 0 on my derivative graph, f prime of x, at about 1/2. I also see that I have a slope of 0 at about 2. So I want to make sure that my derivative graph has a 0 at 2. And then I have another 0 at about, we'll say that's about 5.5. I know it's not exact. 3, 4, 5, 6. Okay, the other thing that your graph of your original function f of x tells us is where f of x is increasing, f prime of x is positive. Okay, that means it's above the x-axis. And where f of x is decreasing, f prime of x is negative. Okay, so if I look at my graph before my zeros, I see to the left of one I'm decreasing, to the right I'm increasing, then I'm decreasing again. So for my derivative graph, I know that I should be negative to the left of my first zero. Sorry, I think I said 1, that should be 1/2. Okay, then I know that it's increasing in between that 1/2 and 2, which means I'm positive, and then at some point I'm going to turn back around because I see that I have that slope of my tangent line is 0. So I need to get back to my x-axis, and then in between that 2 and 5.5 slope right in here, I see that I'm decreasing, which means I am going to have my graph be negative. And then that's all we need to know for that first example in 2.8. Okay, your slope, or not your slope, your derivative for the next example. If f of x equals x cubed minus x, find a formula or an equation for f prime of x. Okay, so back to your limit definition of a derivative. We're looking for f prime of x. So I have the limit as h approaches 0 for f of x plus h minus f of x equals h. That's your general notation. Now when I use I'm plugging in my function for this problem, what that looks like is h approaches 0. F of x plus h, so wherever I have an x in my original function, I'm substituting x plus h into that. So I have x plus h cubed minus x plus h. Okay, that is for my first piece of my limit definition. From there, I'm subtracting f of x, which is just my original function. So subtracting x cubed minus x, and I'm putting that all over h. Okay, when I expand this, I have the limit as h approaches 0. Again, this x plus h means that you're multiplying this to itself 3 times. So you might want to do scratch work, double check my work. When you do this on your own, I will expect to see this, but for space purposes, I'm going to give you guys what this looks like. So I have x cubed plus 3x squared h plus 3x h squared plus h cubed minus x minus h minus x cubed plus x. So that's the entire numerator expanded. That's also including distributing this negative to my f of x function. That's all over h. Again, for this method, anything that does not have an h should eliminate. So I have an x cubed and a minus x cubed. I have a minus x and a plus x. And I think that's everything that cancels in that step. Then what's left over is 3x squared h plus 3x h squared plus h cubed minus h all over h. I can factor out an h, or you can do this in one step. You see that you have an h in every single term for your rational expression here. So I can eliminate a single h from each term. And what you have left over is h approaches 0, 3x squared plus 3xh. Where are we at? Oh wait, this one should not have been cubed. That's where I'm getting lost. Or yeah, it should have. Okay, then that becomes a 2. And we have plus h squared minus 1 all over h. That all over h should have eliminated actually. So now I can evaluate when h is 0. So those two terms cancel out. And you're left with 3x squared minus 1. That is your derivative. Okay, so then if I ask you to evaluate at a specific point, you could do that. The rest of these we will go over on Tuesday, and then I have a YouTube video that we will watch as well for this example here with your absolute value.